These are the example exercises for the beginning of Unit 2, Freefall and Projectile Motion. So first we will start with a freefall example with no horizontal displacement. A ball is released from a height of 10 meters. How long did it take to reach the ground? How fast is it traveling when it reached the ground? So the first thing I want to do in this problem is list my variables. I have my acceleration due to gravity as g equals 9.8 meters per second squared. I have a peak height of dy equals 10 meters. And how long did it take to reach the ground? So I have a time variable that I want. And I also have a second part. How fast was it traveling when it reached the ground? That'll be Vy. So to calculate Vy, I need time. So there's two variables in that formula. So I'm going to start out with the peak height. How long did it reach the ground? So if I start out with the formula dy equals 1/2 gt squared, and I plug in my variables, 10 equals 1/2 9.8 t squared. Now I just need to finish doing the math. 10 equals 4.9 t squared. T squared equals 2.04. So time equals 1.43 seconds. That's the first part of this problem. It takes 1.43 seconds for this ball to reach the ground. Now that I know how long it took to reach the ground, I can find the final velocity at the bottom, and that's the formula Vy equals gt. So now plugging in that time variable, Vy equals 9.8 times time, which is 1.43. So Vy equals 14 meters per second. For the next example, a brick falls off a roof while a building is being built. It falls for 9 seconds. How tall is the building? So let's list our variables out again. We have gravity's acceleration is 9.8 meters per second squared, and we have a time variable of 9 seconds. And it asks me how tall is the building, so I'm looking for dy. So I'm going to use the formula dy equals 1/2 gt squared, where I'm solving for dy. Put my variables in, and this time 9 squared. So I have dy equals 4.9 times 81. dy equals 397 meters. That's pretty tall for 9 seconds of falling. Okay, now a horizontally launched projectile problem. A ball rolls off a table with a horizontal velocity of 1.5 meters per second. The table is 0.7 meters off the ground. How far away from the table will the ball land? So first, I'm going to actually draw a picture. This is my table. Now the ball, when it initially leaves, is going to be traveling with an x velocity of 1.5 meters per second. It's going to travel in a parabolic motion to the ground and hit. Now, if I look at the vertical height right here, that's my dy. And that is 0.75 meters. This right here is dx, and that's what I'm looking for. That's the variable that I'm looking for. Now, I have gravity's acceleration as 9.8 meters per second squared. And if you look in my picture, I have all my variables listed. So sometimes a variables list can be seen inside a picture. So I'm going to now look at what I need. How far away will the ball land? That is the dx equals vx times time formula. That's how far away it is, the dx. But in order to find time, since it's a variable, I need to look at some of my other variables. I have dy and gravity's acceleration, so I could do dy equals 1/2 gt squared, 0.75 equals 1/2 9.8, oops, that's a t squared. Now, 0.75 equals 4.9 t squared. So t squared equals 0.153, which means time equals 0.39 seconds. That's how long it will take to fall to the ground. That's also how long it will take to go horizontally. It's the same variable for each, the amount of time it takes to reach the ground, the amount of time it takes to go horizontally. So I can use that now in my dx equals vx times t formula. So dx equals, remember it left at a velocity of 1.5 meters per second, and my time is 0.39 seconds now. So my dx is 0.587 meters. Remember that x displacement is vertically down from where the ball left the table. While it's on the table, it's not in projectile motion, but as soon as it leaves the table, it's in projectile motion, and that's where your dy is. That's where your dx is measured from. So make sure you're familiar with that. The last problem is an angled projectile problem. A cannon fires a cannonball at an angle of 40 degrees with a velocity of 100 meters per second. How high is the ball's peak height, and how far away does the ball land? So first, again, I'm going to draw a picture, and this is going to be a good picture. I have my ground. Down below here I have my cannon. Now the reason I drew the cannon below the ground was so I could have the ball leave at ground level. So this ball is going to go up, travel parabolically, come back down, and land. So if I cut this in half where the peak height is, I have this as my peak height, dy. I have a velocity coming out of the cannon of 100 meters per second. That's my v, just v. And my angle is 40 degrees. And if I look at this, this is my total displacement dx. Now, the interesting thing here that I want to point out that will become important later on is that when this ball lands over here, the velocity it was at in the beginning of 100 meters per second at 40 degrees is going to be the same thing over here except downwards. This will be 100 meters per second, and this will be 40 degrees. So what goes up must come down in the same way in this case. So when I find the components of that velocity over here, when I find the x and the y components, those are going to be the same components over here, just my y component will be pointing down now. So let's look at this problem now. I have a velocity and an angle and gravity's acceleration, and that's it. So in order to find how high the ball's peak height is, I need a free fall time. And in order to find that, I'm going to have to find a vy velocity. So let's take a look at that initial velocity setup. We have a velocity of 100 meters per second, and that is at an angle of 40 degrees. Now if I draw a vertical line and a horizontal line from that, we're using the parallelogram rule of vectors. I can draw an x component and I can draw a y component. Now remember, if I translate that y component from here over to here, it helps me form a triangle where I had an angle of 40 degrees. So those trigonometry formulas come in where I have Vx equals v cosine theta. So I can solve for my x component. Let's do that right now. 100 times the cosine of 40 degrees, and that gives me an x component of 76.6 meters per second. And Vy equals v sine theta, so Vy equals 100 times the sine of 40, So Vy equals 64.3 meters per second. So now I have my components of these velocities. It's going to be important, and you can see I've got a Vy, which means if I have a Vy and gravity's acceleration rate, I can find a free fall time. So let's go to a new slide and we'll take a look at how these formulas come into play. So first I have to look at how the angled projectile problem is set up. The amount of time it takes to get from the launch to the peak is the same as the amount of time to get from the peak back to the ground. It's kind of a mirror image. So if I think just in the vertical direction, the amount of Vy velocity this cannonball will gain as it falls from the peak to the ground, that Vy, if you remember, we had as 64.3 meters per second, and gravity's acceleration rate is 9.8 meters per second squared. So we can calculate how much time it will take for the ball to reach the ground from the peak to the ground based on its y motion. So let's do that now. Vy equals gt. So 64.3 equals 9.8 t. That's a t. So my time is 6.56 seconds. That's how long it will take to reach the ground from the peak to the ground. If I doubled it, I'd have the total flight. But I don't need it doubled for the vertical parts. So I'm going to do now dy equals 1/2 gt squared. Dy equals 1/2 9.8, and now my new time variable t equals 6.56, and that'll be squared. So dy equals 210.86 meters. I have my first answer to this problem. I have my peak height. Now, I also want to know from this problem the horizontal displacement of this, the total horizontal distance it travels. So now that I have my time variable, I can do dx equals vx times t. And if you remember from over on the other slide, my vx was 76.6 meters per second. That's my x component. That's how much in the x direction this projectile is traveling. So my new time variable of 6.56 seconds will help me solve this problem. So dx equals 76.6 times 6.56. So dx equals 502.5 meters. Now remember, that's only for one part of it, only 1/2. This, all I've been solving for this whole time is from the peak down, from its highest point down to the bottom. I've got to double that now in order to get my total rise and fall. So 502.5 times 2 gives me a dx total of 1,005 meters. Now, that's an angled projectile launch from the same launching height to the same landing height, so ground level to ground level. During our meeting tomorrow on Wednesday, I will show you how to do a multi-leveled launch where you either launch from lower than where you land, or if you launch from higher than where you land.